we're about to dive into one of the most interesting and honestly counterintuitive puzzles in all of AI. And that is, why does giving a model more senses, like sight and sound, sometimes make it, well, dumber? Today, we're going to build the deep intuition to really understand the multimodal mind. Okay, let's just start with a puzzle that I am sure has frustrated a lot of you. So you've got this amazing state-of-the-art vision model. You've got a powerhouse language model. And you think, I know, I'll combine them. I'll create a supermodel. You feed it images, you feed it text, and instead of getting smarter, it just breaks. It starts totally ignoring the images, or maybe it ignores the text, or it just gets hopelessly confused. So why? Why does adding more information, more senses, sometimes lead to less intelligence? This is the core problem we're going to unravel together. So to get to the bottom of this, here's our game plan. First, we're going to really frame this puzzle and see why it matters so much. Then we'll build up from the very first principles, figuring out how models can learn a shared language. We'll look at the different blueprints, the architectures that let this conversation happen. We'll uncover the one big breakthrough that changed everything. And finally, we'll see these incredible models out in the wild. All right, so let's properly set the stage, because this isn't just some academic thought experiment. For anyone out there actually trying to build these systems, this is a very, very real roadblock. If you have ever worked on a multimodal problem, you know this feeling deep in your bones. You spend all this time carefully preparing your image data, your text data, maybe even audio. You feed it all into your network, and what happens? The model develops what's called unimodal bias. It essentially learns to cheat. It just finds the easiest path to an answer by only listening to the text or only looking at the images, and it effectively ignores one of its senses. It's like having two brilliant experts in a room who just flat out refuse to talk to each other. This is the challenge we have to overcome. Okay, so let's start building the solution. To figure out how to fix this, we have to go all the way back to the fundamental nature of the problem, and it really all comes down to language and translation. The first big idea we need to get our heads around is alignment. The best way to think about this is that we're creating a Rosetta Stone for the AI. See, a vision model speaks the language of pixels and color values, while a language model speaks the language of words and grammar. They're completely different languages. Alignment is the whole process of creating a shared dictionary, a common ground, so that the concept of a dog represented in an image means the exact same thing as the word dog in a sentence. We're building a bridge between these two worlds. Before we have alignment, our models are basically like two world-class specialists who are locked in separate soundproof rooms. The vision model can look at a million photos of dogs and become an absolute expert on what they look like. Floppy ears, wagging tails. The text model can read every book ever written about dogs and understand all the nuance of the word dog. But if you ask them to work together, say to find a picture of a fluffy dog catching a frisbee, they're totally useless. They have no common ground to collaborate. Now, what's so cool here is that this problem has a geometric name, the modality gap. See, when we train these models, they learn to map all their data into this giant, high-dimensional space. You can think of it like a massive library where similar concepts are placed on nearby shelves. So an image of a dog becomes a single point in this library, and the word dog becomes another point. The modality gap is this key insight that if you don't do anything special, all the image points will naturally cluster in one corner of the library, and all the text points will cluster in a totally different, separate corner. They form these two distinct clouds of meaning, with a literal gap between them. So, if alignment is all about creating that shared language, the next question is, how do we design the room where these models can actually have a meaningful conversation? Let's take a look at the blueprints for how these models are built to talk to each other. And this brings us to our second key idea, fusion. If alignment is the act of translation, fusion is the conversation itself. It's the process of actually taking the information from the different senses, now that they're speaking the same language, and merging it to form a single, richer, more complete picture of the world. It's the moment where seeing a dog and reading about a dog combines to create a deeper concept of dogness than either sense could ever get on its own. And we can try to have this conversation at 3 different stages. We could try data-level fusion, which is basically just mashing raw pixels and raw text together right at the beginning. Or we could go to the other extreme with output-level fusion, where we let each model come to its own conclusion first, and then we just try to average their final answers. But the real sweet spot, where the deepest, most interesting stuff happens, is often feature-level fusion. This is where each model processes its own data, extracts high-level concepts, things like shapes, objects, sentiments, and then these rich features are combined for some really sophisticated joint reasoning. And this diagram here illustrates brilliantly how those strategies become real architectures. On one side, you've got the two-tower model. Here, the image and the text are processed in their own separate parallel towers, and they only meet up at the very, very end. It's a pretty shallow conversation. But on the other end of the spectrum, you have the one-tower model. This is where image and text features are thrown together and processed jointly in a single unified network from a much earlier stage. This is where true, deep, multimodal reasoning can really happen. So we have our two key ingredients. We have alignment, the translation, and we have fusion, the conversation. But for years, the field really struggled to make this work reliably, and it's because researchers were getting frustrated by having the order of operations completely backwards. For a long time, the prevailing wisdom was this. Look, let's just extract some features from our image, some from our text, we'll just stick the vectors together, concatenate them, and we'll feed them into a really big, deep neural network. It's powerful, it'll figure it out, right? But what happens in practice almost every single time? The network takes the path of least resistance. It finds whichever modality is just a little bit easier for the task, latches onto it, and then learns to completely ignore the other one. And whoom, that's how you get that unimodal bias we talked about. You're asking these models to have a deep philosophical conversation without first teaching them a common language. It's just doomed to fail. And here, this is the click. This is the aha moment. This is probably the single most important idea in this entire field. You must align before you fuse. You have to translate the modalities into a shared space of meaning first. It's only then, once they are actually speaking the same language, that you can have a meaningful conversation, a meaningful fusion. Trying to fuse unaligned representations is like asking two people who speak different languages to write a novel together by just mashing their words randomly onto a page. It's not going to work. It's just noise. Alignment creates the common ground that makes everything else possible. So, how do we actually do it? How do we achieve this alignment? The breakthrough technique is called contrastive learning, and it's just an incredibly elegant and powerful idea. Here's how it works. You take a bunch of data, let's say an image of a dog and its matching caption. That's a positive pair. Then you take that same image and you pair it with every other caption in the batch. Those are all negative pairs. The model has one job, and one job only: learn a force field. It has to physically pull the representations of that positive pair closer together in that high-dimensional library, while at the same time it has to push the representations of all the negative pairs as far away from it as possible. And the way this whole push and pull dynamic works is through a mathematical rule called a contrastive loss function. Now, don't get hung up on the formula on the screen. Just think of it as a set of rules for organizing our geometric library. For every positive pair, the image and its real caption, the rule says the distance between you two must shrink. It must get as close to zero as possible. It's a powerful attractive force. And for every negative pair, the image and a wrong caption, the rule says the distance between you must be greater than some minimum safety margin. It's a powerful repulsive force. And over millions and millions of these examples, this simple push and pull game completely reorganizes the entire space, bridging that modality gap and forging the shared language that we need. So that's the core theory: align with contrastive learning, then fuse for deep reasoning. Now let's see how this one powerful idea has completely transformed the landscape of real-world AI models. I mean, this timeline just tells such a clear story of progress. The early days, around 2019, it was all about just getting multimodal pre-training to work at all with models like Viobert. Then, right around 2022, you see this explosion of models like Blip and Coca, which had really mastered this align then fuse paradigm. And that foundation led directly to where we are right now, where the entire field is shifting to plug vision and other senses directly into large language models, which is giving us these incredible versatile systems like Blip 2 and QNVL. Each step was really built on the last. And one of the most mind-bending examples of this is a model called ImageBind. It takes this idea of alignment to an absolutely incredible extreme. It aligns 6 different modalities. We're talking images, text, audio, depth maps, thermal camera data, and even motion sensor data, all into one single unified space. The way it does this is by using images as the central Rosetta Stone, learning to align every other sense to the visual world. But here is the most amazing part, something researchers call emergent alignment. Because everything is aligned to images, the model can start making connections between senses it was never explicitly trained on together. For example, it can find an audio clip of crashing waves just by being given the text ocean waves, even though it never saw a single text and audio pair during training. It's a truly amazing emergent capability. So, if you're going to take away just 3 things from our journey today, let them be these powerful mental models. Number 1, align before fusion, always. You have to translate before you can have the conversation. Number 2, the whole goal is to bridge the modality gap. Your job as someone building these things is to be a geometric architect, to organize this high-dimensional space of meaning. And number 3, architecture follows strategy. A simple 2-tower model might be perfect for simple retrieval, but you're going to need a unified 1-tower for that deep, joint reasoning. The structure you choose depends entirely on the kind of conversation your model needs to have. We've spent this whole time understanding how an AI can learn to see and read and listen in this unified way, how it can comprehend the world through multiple senses. But that just naturally leads us to the next great frontier, doesn't it? Now that these models can understand, how do we build models that can create with multiple senses? How do we go from describing a video to generating a brand new one from just a simple text prompt? That is a question that's going to define the next chapter of this incredible field.